Lead is completely passive. They have an intrinsic advantage, and you can use to make very compact reactors. The nuclear industry produces millions of tons of waste. You can use this mix in a fast reactor for making energy.
This is Energy Cast, and I'm Jay Downhauer. Today we're talking about making the most of MOX and lead. I've now covered 4 companies with unique small modular reactor designs for producing megawatts of clean nuclear energy. Each of these guests has a slightly different approach. I found that nearly all are using a form of a technology that has been proven before. Today's guest is miniaturizing a design called a lead-cooled fast reactor. They were used by Soviet submarines for a brief stint during the Cold War, so you may have missed it. Instead of pressurized water, which most reactors today are using, my guest is surrounding their nuclear reaction with liquid lead. He claims this design is ultimately lighter than water. If you don't have to contain all that pressure, he says, the walls don't have to be so thick. They're also able to shrink the size. Among the guests I've profiled, they're proposing what's probably the largest small reactor I've seen. Size is key for SMRs because their advantage is they can be built at a factory and shipped to site rather than built out there. This should also decrease the complexity of design as complicated as one required for nuclear power. The second part of this design focuses on the fuel. My guest wants to power their SMRs with mixed oxide or MOX. The advantage is that a MOX fuel reactor is like a billy goat. It'll eat anything, including all the spent nuclear waste. That's important as spent fuel continues to add up. My guest says they're the typical policy and regulatory challenges his peers are seeing all over the world. But the one thing he's not worried about is the technology. Here's hoping his light liquid lead reactors play a heavy role in our nuclear future. My guest today is Stefano Bueno, CEO of newcleo, a small modular reactor developer headquartered in England. Stefano is Italian, and they are currently making things ready for a test facility in Bologna. We discussed the benefits of lead in their design, as well as the clear advantages of MOX if policymakers would just do the right thing. Why is this so hard? I was also curious how challenging this is becoming from a business perspective. SMR developers like newcleo already have their permits. It took them years, and newcleo was founded just 2 years ago. Also, this kind of technology takes years to develop and billions of dollars. As more players get into the space, is it getting harder to find investors? I think you'll be just as surprised as I was. I hope you enjoy my conversation with Stefano Bueno. We're here with Stefano Bueno, CEO of newcleo. And Stefano, I've spoke to several SMR developers, NewScale, Last Energy, Oklo, and I think it's important to explain that while there are small modular reactors, they all have different strategies. So what is newcleo's?
Of course, the first difference is the cooling system that we are using, that is lead. I think this brings a lot of advantages compared to other technologies in terms of cost and also safety, I would say. With respect to the application, we have a 200 megawatt electrical producing unit that can be clustered in groups of 4. We might use the same technology to make a microreactor of 30 megawatt electric, and this can have industrial applications. So the strategy overall is everything is applicable to the fact of it being small and modular.
I don't know very much about lead-cooled fast reactors. What are they? And you said they're safer, too. So how does that work?
It's very easy. It's a liquid metal, and liquid metals have been used in the past in the nuclear industry, but sodium. The difference between sodium and lead is essentially that sodium has a chemical risk. Sodium gets fire in contact with air and water. So to do sodium reactors, you have to spend a lot to safety systems, so they become too expensive. In France, for example, there has been sodium reactors that have been developed, and this has proven to be too expensive. So the industry was abandoned for this reason. Lead is completely passive. You don't have any chemical risk. They have an intrinsic advantage, and you can use to make very compact reactors. That's the big difference. But they are both fast reactors. And the real advantage of fast reactors is that you can close the fuel cycle. You can make multiple use of the uranium that is being extracted by the ground. You can even reuse the nuclear waste. Normally in a reactor, reactor, you use, I would say, for every gigawatt electric, more or less 200 tons of uranium to make more or less 24 tons of fuel. And of this fuel, you essentially fission less than 1 ton. Fast reactor, you can imagine a cycle in which you recycle all of the uranium that you extracted from the ground. So you might have an efficiency with respect to the fuel of 200 times more. Since the nuclear industry produced millions of tons of waste, not only uranium, but also the plutonium and the radioactive waste, you can use this mix in a fast reactor and use it for making energy if you join these kind of reactors with the strategy that closes the fuel cycle.
Are we having to reprocess the fuel in any way?
Yes, you have to reprocess. This has been done in many countries. Today, the only country that is still reprocessing the fuel is France, because France has been using mixed oxide fuel that is made out of the nuclear waste, essentially plutonium and uranium from the previous cycle. MOX was used in the sodium reactors, and indeed, we are taking exactly the same kind of fuel that had been radiated for many, many years in the French reactors. So we are not reinventing around the fuel beans. But since this industry was developed and the sodium was abandoned, EDF is still charging the reactors 10% of the fuel with MOX. So the MOX industry has survived. The only difference is that when you irradiate MOX, you can do it essentially only one time in water reactor, water cooled, because you build up the heavy elements that have a very long half-life, like plutonium, americium, curium. And you are also creating some elements that are no more fissionable using the spectrum that is present in water reactors. So you have to use fast reactors to be able to break all of these heavy atoms. Otherwise, you accumulate them. The French system is still working on that, but they can use the reprocessed fuel only one time. With a fast reactor cycle, you can use multiple times. So this is a huge opportunity because we can essentially eliminate all of the plutonium that has been reprocessed in our history, including the one that has been reprocessed for making bombs, essentially. We can also use the uranium that has been irradiated and is so no more uranium-235. That is the fissionable part in the spectrum, but you can still use this depleted uranium or even the uranium that has been irradiated and is part of the processing. So yes, you need the processing, but France is doing this, Japan used to do it, UK, many countries used to do this. So there is a lot of know-how, Belgium and Europe as well.
What about the United States? What would be the strategy here for this?
Yeah, unfortunately, the policy changed in the country. So at a certain moment, the United States have decided to reprocess and make MOX. So there has been a huge investment that was done in building MOX manufacturing facility in the US. The facility was ready to be used, but it was shut down during the Trump administration. Honestly, I don't know the details of the reason why it was shut down. But clearly, there wasn't behind this strategy reactors that could actually burn and reuse this fuel. So there wasn't probably not also the technology that can make the best use of this one. At the moment, you cannot reprocess the fuel in US, and the MOX factory has been abandoned, which is very sad because I believe that with the new wave of technology that is coming, we are not the only reactor that can use this MOX. Even the sodium reactors proposed by TerraPower can use MOX. So indeed, this is an option, still an open option, but the current policy is not providing this opportunity. I must say that there is something also strange for us European in US. Essentially, the responsibility of the disposal of the nuclear waste is in the hand of the government, while most of the European countries, the company that is operating the reactor is responsible of the waste until the end of its life, for 1,000 years in the case of plutonium. There is more responsibility, more willingness to close the fuel cycle probably in Europe than in US, where there is no responsibility essentially on the nuclear waste. It's all on the shoulders of the government.
One of the companies I talked to who was developing an SMR was Last Energy. They essentially said the regulatory authorities in the United States are too difficult for them, so their go-to-market strategy was to secure contracts in other regions like UK, Poland, Romania. Are you seeking a license from the U.S. Nuclear Regulatory Commission, or are you going to try to commercialize in other countries first?
Well, it all depends because it all depends on the technology that you are proposing. Of course, if you have to, for example, qualify a fuel, we know that in US it might take a very, very long time, but in other cases, maybe the time is shorter. Honestly, I don't think there is much difference between regulatory authorities in different. We have engaged France, which is known to be by far one of the most difficult authorities in the world. For example, France decided to increase the safety standard after Fukushima of its EPR, and this is one of the reasons why the EPR project got delayed, because during the construction they had to reconsider many aspects because the authorities required the reactor to increase of a factor of 10 all of the safety regulations. So it's a tough country. But I believe that once you have a very safe design that has been authorized in a country, either there will be probably some harmonization, especially in Europe, or you have to consider to engage in every country. We certainly at a certain moment want to engage into US, and we will. We only have to clarify if we can be able to use the MOX, if it makes sense to bring our fuel from Europe, for example. We'll have to clarify, I would say, more from the economic point of view, if this is a valid option for US.
Sure. You said this is a fast reactor. How fast do you believe you can have a commercial unit operating? NewScale has been around since 2007. They received their NRC permit just last February, 2023. newcleo was founded in 2021. How fast do we think we could be commercially operating anywhere?
Realistically, we have a plan to make our first reactor in 2030 operational. That means also our first manufacturing facility for the fuel, because we want to have our own manufacturing facility. There is a small capacity in France at the moment, and our design is coming from the experience from the past, but it's a novel design in terms of the assembly, the fuel assembly. So we need to have our own manufacturing. But this fuel will be exactly the same than the commercial one. We have a good advantage. We are planning next year to start for our commercial unit. So the first reactor is a demonstration reactor that will have embedded all of the solution of the commercial unit. It's kind of a validation unit. And we want to use this reactor also to make improvements on our industry in the future. Namely, we want to develop the material that can withstand very high temperature using lead, because lead has a very high boiling point, 1,700 degrees Celsius. You can go very high in temperature if you have the right materials. We will use this reactor to make our materials evolve as a test reactor. But our first commercial unit will see hopefully the light in 2032. And we will start in the generic design assessment in UK next year to be able to be on time for that moment. From there on, of course, we will be building all of the supply chain, which partially is verticalized. We are actually building many components. We will be building many components. We have already 3 manufacturing facilities that we acquired through acquisitions in this case, and we will give the possibility to this manufacturing facility to evolve their skills in order to make also the components for our reactor. So we'll be ready for 2032, but we will be able to duplicate this design very rapidly, so to deploy a fleet efficient way.
Stefano, one of the things that was interesting to me, and you mentioned this at the very beginning, you're developing a 20 megawatt equivalent unit and a 200 megawatt unit. The 200 is on the larger side of SMRs that we've seen. NewScale's design that they got approved was 77. What can you tell us about these two designs? And this 200 is something I pitched before this episode, a 200 megawatt reactor. Is that still modular?
Yeah, it's large in power, but small in dimension, because the biggest component of the reactor will be the vessel that has a diameter of 6 meters and a height of 6 meters. So you realize it's very small. We have just manufactured in one of the facilities we acquired a vessel that is essentially bigger in volume for a test facility in Europe that will be used. So it is really the dimension that can be transported, no doubt. 6 by 6 by 6 is possible. And this is the biggest one. Of course, all the other components are much smaller. We have essentially 3 pumps and 3 different steam generators. So the other components are smaller. If the biggest component is transportable, the rest should be straightforward.
Yeah, so it's on the larger side of small modular reactors.
For the power, but also a high temperature cycle has a higher efficiency. The thermal power is 470 megawatt. This is thanks to the property of lead, because lead has a density 10 times higher than water, has a very good shielding properties with respect to radiations. So you actually can make much smaller components for this reason. With the same volume that you deploy of steel, that you deploy with a pressurized system like the one of newcleo, we essentially need, for the same power, half of the steel. You understand that the component is really manageable. A component of 6 meters is not even as high weight because we are not working under pressure. Our vessel is very thin as compared to what a pressurized water reactor has to have. That's very important because it makes manufacturing also easy.
Is there any upper limit to small modular reactors when you were sizing this and determining what could be modular? I know you've probably been told or done studies that have said, like, this is a limit.
No, I think it has to be the limit of really transportability and handling of the components and so on. For example, Rolls-Royce is claiming to be able to transport this big vessel. Maybe it's quite complicated, it's quite big, but it's still, I would say the limit is when you don't have to do manufacturing operation on the site. You can build it, qualify this component in the factory, and then you ship and you assemble. That is, I think, where the real definition is. The best is for the system because you can transport with less cost, because then you have to optimize everything in a small modular reactor.
Stefano, I've spoken to a number of leaders in this space, not only small modular reactors, but nuclear industry in general. And a lot of the utilities have made net zero carbon pledges by 2050, right? And what most of the nuclear guests have pointed out is that right around the time we hit 2050, most of the existing nuclear plants in our fleet, there's about 90 of them right now, they're going to age out, even the ones that I think have had licenses extended. So that's going to create a huge problem for being carbon neutral, right? It's going to be quite a lot for even renewables to overcome. So what do you think about that? Do you believe SMRs like yours can come online in time? You talked about 2030 to replace that much capacity that is large scale nuclear. Each one is about 1,000 megawatts or more at each facility.
Yes, I think so for many reasons. The fourth generation of nuclear is supposed to be safer. And this reflects also on the dimension of the sites where you can build your reactors. We can build 800 megawatt electric capacity on slightly more than 10 hectares of land. So you can already think of a strategy in which you install smaller machine on the land of the existing reactors. I just visited 1 month ago Super Phoenix, so this large reactor that is in the south of France, close to Italy and Switzerland. And the site is 170 hectares. There was a huge space that was dedicated to these reactors in the past because the fear of accidents and so on. So if we have less power, more safer reactors, you can already start occupying this site. So essentially, you might think that you might substitute even the larger installation with a number of small modular reactors. It is true that there is an urgency for 2050, which is not only regards the nuclear, every kind of energy that is carbon free. And I think there is not even a competition ongoing between the different technologies. We need all of them. We need dispatchable nuclear energy. We need other forms of energy because we really have to go fast. I think that having a multiple companies, reactors and investments that are done in different technology is an opportunity for a faster deployment, not really for a competition, I would say.
Speaking about competition, again, I've spoken to a lot of SMR developers, and this isn't inexpensive to develop a nuclear reactor by any stretch. So I'm curious, are we starting to see it get very crowded? Is it almost getting too crowded? And I'm thinking about this as far as your ability to get funding for this research, because it's a long timeline between now and being able to get a fully commercial unit. Is that becoming challenging? And also, do you think that we're going to get to a point where it's going to be harder to come in and say, I've got an innovative SMR design? Are we starting to get to a saturation point?
No, I think there will be a natural selection of the technology, not because the good or the bad of the technologies, but by the capacity of the execution of the team, the strategy. I mean, there is any reason why a company can be successful or not. Certainly, having access to money is very important. We had the chance to have raised 400 million in the first 2 years of operation, and we are already anticipating estimating another $1 billion of capital increase in an operation which is ongoing, and we don't see any criticality in raising this money. Of course, we have the chance to have a technology that might seem odd to you because it's never been used in US, for example, but it's been used in the past in Europe. The Russian army had 10 submarines that were made out of lead, and Europeans in the 90s have exchanged a lot on this technology with the scientific, and so they know a lot of this initial experience on this kind of reactors. And Europe has been a large activity and research going on lead, so it's ready to use technology. So we have this advantage that we think we have a very competitive and very mature technology, and also a lot of credibility as a team, myself as an entrepreneur. So I was able to have access to a lot of capital. This is part of the selection, unfortunately, the accessibility to the capital. It will be natural. I hope that many companies may have success, especially because I see strategies that are even complementary. Many small modular reactors aim at serving a completely new market, which is the one of industrial districts, big consumers of electricity with small capacity. But we need so much energy that we really need all we can build. In Europe, we think we have to triple our production of electricity between here 2050, especially because of the use of batteries into cars. We really have to work all together. And we have to have different strategy. We have chosen a more of an independent strategy, so we don't feel the competition very much because we want to build and operate the reactors in certain countries. So we are not in a rush to trying to sell the technology. We're going to build the technology, operate the reactors, and then on the basis of the economics of our operation, I think we can be successful in expanding these reactors everywhere, but we still have to prove it. So we'll be part of the competition.
The episode just before this one, we talked a lot with my guest about the need for more transmission. And the United States is actually predicting that in order for us to be 100% clean energy, we need to build triple the amount of existing transmission infrastructure in this country, which is very hard, especially when you get to questions like permitting. And the reason for that, of course, is because there's this assumption that most of the clean energy is probably going to be renewable. It's going to be smaller. It's going to be more distributed. And so enter small modular reactors, and especially something like your design where you say you can cluster your 200 megawatt offerings. That's not a small plant. You're back to large power plants at this point. What do you think about that? I mean, this has to be part of the conversation, because I think what's probably going to end up happening is, yes, we're going to have a lot of renewable energy, and yes, it's going to be more distributed, but there becomes a pain point where it's going to be more and more difficult to tie it all together, especially with its small generation. Don't you think?
Yeah, exactly. That's the reason why you have to be completely flexible. In the case of Europe, for example, if you have to replace 1 gigawatt and the distribution is already there, nothing better than replace the same power. I think the real challenge is that we have to substitute the gas. And the gas is dispatchable, programmable energy that is really compensating the solar and wind. And you have a bigger compensation that you have to do during the day, and small compensation if you have, the clouds and something unexpected that happen. So I think this is another opportunity of the small modular reactors. You can build some smaller thermal capacity in the system to be able to modulate the electricity during the day to counterbalance the need of electricity that is higher during the night and even in the morning. And well, solar and wind sometimes create an unbalanced market and very high prices. So I think we have to build and to think of innovation not only inside the reactor, but also outside the reactors and BOP in the balance of plant, and build our system in a very flexible way. So the modularity can help placing smaller or larger cluster unit where it is needed by the grid. And the machine themselves, they should have the flexibility to modulate their power by keeping the reactor power constant in order to adapt to the need of the grid. And sometimes the reactor maybe at the speed the gas turbine could react if there is an immediate need to the grid to compensate, which is a real challenge. It's especially for thermal reactor. We have again the chance to have fast reactors, so they can be even switch off and on much faster procedures than thermal reactors.
Well, that's very interesting. I'm always interested in the idea that you can ramp up the units, right? How difficult is that? It would almost seem like something like that would have to maintain an amount of heat, right? Can a cluster of them ramp up like a natural gas plant?
Yes, of course you have to maintain a heat capacity that may compensate for a higher work of your turbine during the day. So you have to have a storage system. But you can build a very simple storage system, easy to operate in your system. This is certainly something that we will need. So we don't have to think of operating a reactor like we did in the past, switch it on, and if it's off, it may stay off for one day because we need to make a very long restart operation. We really have to think of a reactor that can provide 50% more electricity in the peaks of the request during the day and maybe 50% less when there is the solar peak in the middle of the day, for example. That's where we want to get.
So, Stefano, it sounds to me like got a lot of work to do. 2030 is in the blink of an eye. So what really is the next step for you over the next few years? What's your immediate concern right now, and what keeps you busy most of the time these days?
My concern is how the company can grow steadily. I don't have big concern about the technology. The interaction with the authorities have started very well because there is a willingness of the authorities to go fast. So the interest seems aligned with one of these new, at least in Europe. So it's really the growth and industrial operation, controlling and creating a supply chain, etc. So it's really the industrial challenge of building everything from more or less scratch. It's a marathon. It's not a sprint. It will take time, but we are going fast and we're proceeding at a very good pace.
Very good. All right, Stefano Bueno, newcleo, thank you so much for your time.
Thank you.
That was Stefano Bueno, CEO of newcleo, a small modular reactor developer. Stefano had mentioned a MOX processing facility in the U.S. That would be Savannah River, based in South Carolina. The facility was going to convert weapons-grade material into MOX fuel, but the project was scrapped in 2019 in favor of a policy to, quote, dilute and dispose the plutonium. Now, yes, that did happen during the Trump years, but it was first proposed in 2017 by the Obama administration. That probably explains why we didn't see a reversal in 2021. As for the future, we shall see. I want to thank Stefano for his time, as well as Sarah Smith Rule at Weber Shandwick for setting this up. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 171. Be sure to join us next week. We'll learn how one of the oldest HVAC companies is taking a new look at energy efficiency. Until then, I'm Jay Downhauer. We'll see you next time.